All right, here's the bell word for this one. Go ahead and take a minute and do that. And here are the three answers for those three problems on the bell work there. And here's our objective. I can calculate the probability of independent and dependent events. Go and take about 1 minute and copy this down, please. So here's a couple definitions for us. It looks like, well, we do use this vocabulary a little bit in this unit, of course, but independent events when something happens all by itself, and dependent events is when something can happen because something else has already happened. It has to have happened already in order for something to be independent. So that usually means that a dependent event is, well, depending on an independent event, because an independent event happens all by itself, and then something else perhaps may happen because of that independent event. It's like a domino effect, right? Harry flipped a penny the given number of times. What is the probability of each of the following random events? Give your answer as a reduced fraction and a percent. Looks like we're going to write this two different ways. But these again are all theoretical. It didn't say that he actually did flip the pennies. We're just going to figure out, I suppose, what should happen. So these are still theoretical probabilities on this one. Okay. Now these are compound probabilities as well. Okay, so he's flipping a penny. We're assuming the penny is fair. Let's go ahead and find our probabilities here. Let's start with number one. The probability of tails and then tails again. So again, this is compound probability. So we'd find the probability of tails and then multiply it by the probability of the second one, which is still tails. Well, the probability of tails, there's two outcomes. One of those is tails, so it's 1/2. And that means the probability of tails again would be the same, 1/2. We're just going to multiply these out, and this will give us the fraction. We'll just have to change it into a percent. This one's easy, though. The numerator is 1 times 1 is 1. And the denominator is 2 times 2 is 4. So 1/4 is our final fraction. But, of course, this would equal, you can use a calculator if you need to, but it's 25%. So there's our fraction and percent for number one. Number two here, it's longer, but I don't think it's more difficult. It's just longer, right? So we'd be looking at the probability of heads, then the probability of tails, then the probability of heads, then the probability of tails, right? So we got to find the probability of each of these, and as it turns out, starting with heads there, it's two different outcomes. One of them is heads. Tails as well is, there's two outcomes, only one of them is tails, but so we're just going to duplicate these. It's just 1/2 each time, and yeah, we're just going to multiply these out, right? So in my, again, let's just write this first as a fraction. In the numerator, I got 1 times 1 times 1 times 1, which is 1. In the denominator, I have 2 times 2, which is 4. Times 2 is 8. Times 2 is 16. Or you'd have 1/2 to the power of 4 if you wanted. So that's 1/16. Let's go and see what we get in the calculator for this one. 1 divided by 16. I get 0.0625. So as a decimal, I won't round this to the 10th just because it's not too hard. 6.25%. So there's our fraction and our percentage for number two. So number three, you'll see a similarity here between 3 and 1 because we're looking for the probability of tails and then the probability of heads. So it's flipping the coin two different times. And we already know the probability of tails is 1/2. But also the probability of heads is 1/2 as well. So we're going to multiply these two together. This will give us the fraction. The numerator 1 times 1 is 1. The denominator 2 times 2 is 4. 1/4. And again, we already know this is 25%. Just like we saw on number one right there. 25% and 1/4. Number four looks like he's going to toss the coin 3 times. First, we're looking for the probability of heads. Then the probability of tails. And then the probability of heads. And again, the nice thing about tossing a coin is no matter what you're looking for heads or tails, it's always going to be 1/2. So we're going to multiply these out. In the numerator, 1 times 1 times 1 is 1. In the denominator, 2 times 2 times 2 is 8. And put that in the calculator. 1 divided by 8, and you get 0.125, which is 12.5%. Again, with the decimal, you're just moving the decimal 2 times to the right from the decimal value in order to change a decimal into a percent. Now, this is where I wouldn't call it trickery, but we have to be very careful with what's happening with these particular fruits. Okay, so let's read through this. We have to read through it a few times to really figure out what's going on, though, okay? So there are 4 oranges, 7 bananas, and 5 apples in a fruit basket. Allie selects a piece of fruit at random, eats it, and then Bailey selects a piece of fruit at random. What is the probability that Allie and Bailey choose the following? It looks like Allie will always go first, and then Bailey will go second, but it looks like order is not really going to matter for us, except we're on 6 and 7 right there. So let's start with number 4. Okay, so again, we got Bailey. We're going to start with Allie first. Allie goes first, and then Bailey will go, right? So there's Allie and Bailey, and we're looking for both of them to choose apples, right? So let's say, what's the probability that Allie chooses an apple first? Okay, because these are independent events, but we're compounding it because we're combining the two. Now, for Bailey, I'll use purple, but Bailey also will choose an apple here. Okay, now to figure out our final probability is we're going to multiply these two out. Okay, and yeah, that means our original compound probability. We could have written this as probability of an apple, first for Allie, and then also an apple for Bailey. So it's the same thing. Now let's relate this to the vocabulary we've just seen, okay? Allie's event, because she's going first, is independent. Bailey's, though, is dependent. We'll explain more on that here in a second, okay? Because when Allie goes to, what is this, basket? Yeah, the fruit basket. When Allie goes to the fruit basket, we'll need to figure out how many total fruits are in the basket first. Okay, so looks like we got 4 oranges, 7 bananas, and 5 apples right there, right? So when Allie goes into the fruit basket, because she's going first, she will find that there is 5 apples to choose from. Out of how many total? Let's see how many total pieces of fruit there are. Let's see if we can. Oh, there we go. Yeah, let's go ahead and figure out how many total pieces of fruit there are, though. And I'm going to specify here in the beginning. I'll explain more on that here in a second. But I do want you to think about why we do need to know that it is from the beginning. Well, there's 4 oranges, 7 bananas. Combining those, that'd be 11 total pieces of fruit. And then adding another 5 to that would give us 16 pieces of fruit. Now, of course, you should be thinking, well, if she sticks her hand in there, shouldn't she be able to tell the difference? Yeah, but we're saying it's random, okay? So just kind of play along with me here. I don't know why she's choosing fruit from a basket anyways, okay? But here we go. So for Allie, right, 5. In fact, I'll try to make that 5 the same color there because Allie's choosing it red. So Allie has 5 apples to choose from out of 16 total pieces of fruit. Now for Bailey, though, she wants the probability of an apple, but think about this, okay? Allie took one of those apples and ate it, right? So how many apples are left first in the basket? That's our numerator. There's 4 apples left because Allie took one and ate it. And also, it reduced the number of pieces of fruit in the basket by 1 as well. So that's 15 now total pieces of fruit there. We do need to multiply these out. And it looks like we could use some cross simplification. You're always welcome to put this directly into the calculator if you'd like. But yeah, some cross simplification. The 5 and 15, that'd be 1 and 3. 4 and 16 would be 1 and 4. In the numerator, 1 times 1 is 1. In the denominator, 4 times 3 is 12. So 1/12. That would be our reduced fraction. I can't simplify that anymore, but I do need to change that into a decimal. So 1 divided by 12 in my calculator, 0.83 repeating. I'll just round this one to the nearest tenth, 8.3 as a percent. 8.3% chance that Allie pulls an apple out and eats it, and then Bailey pulls an apple out as well. So I'm going to try to keep the colors fairly consistent on number 2, right? So I'm saying Allie's choosing whatever she chooses here in red. Bailey will choose whatever she chooses in purple. So number 5, though, says both choose a banana, right? So Allie's first going to choose a banana. And then it looks like Bailey will also choose a banana. And we want the probability that both pull out a banana. So first for Allie, with the bananas, again, there's still 16 pieces of fruit when Allie goes to the basket, and it looks like 7 of those are bananas. Now, again, we're going to say that when Allie pulls that banana out, she's going to eat it, which means when Bailey goes to the basket, again, there's only 15 pieces of fruit in there because the one that Allie took out is still out. She ate it. But also the bananas is reduced by 1. So instead of there being 7 bananas, 1 was eaten by Allie, and so now there's only 6 bananas total in the basket. And I see a little simplification on this, but I don't know that's going to really help with the 6 and 16. That'd be 3 and 8 right there. Yeah, I don't really think that helps, but it does give us a little simplification. Oh, yeah, it looks like the 3 and 15 would simplify as well. That'd be 1 and 5, so that helps. So for the numerator, I'd have 7 times 1, which is 7. In the denominator, I'd have 8 times 5, which is 40. 7/40. Let's just change that into a percent. First into a decimal using the calculator. So 7/40. What do we get? 7 divided by 40. Enter. I got 0.175, which changes into 17.5%. So the probability that both of them pull out a banana with this Allie's or Bailey's being dependent on Allie's is 17.5%. So a quick note again on the independent and dependent events. Of course, Allie's going in as an independent event, but because Allie's going into the fruit basket, Bailey's probabilities are depending on what Allie is doing in the basket, right? Because when they both choose, let's say the apples, right? Allie goes in, of course there were 5 apples in the beginning, 16 total pieces of fruit, but when Bailey goes in there, it depends on what happened with Allie because she chose an apple. It changed the numerator for Bailey, but also the denominator as well because there's 1 less apple, 1 less piece of fruit. Same with the bananas on that. Okay, so we'll have to keep this in mind as we look forward because now on number 6, it's changing the probability, right? So on this one it says Allie chooses an apple and then Bailey chooses an orange. So I'm going to keep these colors the same. Red is for Allie, purple is for Bailey. And Allie is going to choose an apple again. You've seen that probability before, that's okay. And then Bailey is going to choose an orange. All right, and we're going to figure out both of these probabilities separately. So first up, for Allie to choose an apple, of course, there's 5 apples in the basket. So it's 5 out of 16 total pieces of fruit. Now when Bailey goes to choose her orange, there are 4 oranges in the basket, okay? But this is where it becomes dependent is because Allie chose, or she took out a piece of fruit. So now there's not 16 pieces of fruit in there, there's 15. 4 of those, though, are still oranges. Okay, so that's why we get to multiply these across. And you can see this kind of is, well, pretty much the same exact probability we saw in number 1. The 4 and 16 simplify. We can cross-simplify those. Same with the 5 and 15. Of course, you're always welcome to just use a calculator on these in order to simplify them, but with cross-simplification, that makes that easy. In the numerator, 1 times 1 is 1. In the denominator, 4 times 3 is 12. And yeah, we've seen 1/12 before. So I'm not even going to worry about putting this in the calculator. It's 8.3%. So it's the same probability when Allie chooses an apple and Bailey chooses an orange as both choosing an apple on that one. And again, that's because of the dependentness of these probabilities. So number 7, it looks like Allie will choose a banana and Bailey will choose a gross mango. Well, I don't think mangoes are gross, but apparently someone does. So let's go ahead and put this in there. Just put the probability in first. So yeah, we'll start with our probability. And Allie first is going to choose a banana. You've seen one of those before. And then Bailey will choose a mango. Now some of you know the answer to this. But I'm still going to show the compound probabilities, okay? So first up, Allie's going to choose a banana, all right? So for Allie, there's 16 pieces of fruit. 7 of them are bananas, right? So there's a good start. But for Bailey choosing a mango, this is where things get a little crazy because, yeah, Allie did take one of the pieces of fruit out, so we're still looking at 15 pieces of fruit. But how many of those are mangoes? 0 of them are. So multiplying this out, I mean, you can simplify it if you need to, but, well, we're just multiplying the numerators and denominators, right? So I'd have 7 times 0 in the numerator, which is 0, and in the denominator 16 times 15. I mean, not that it's going to make any difference, but 16 times 15 looks like it's 240. And yeah, this can be simplified into just a whole number that looks like a whole. It's 0, and 0 would also be, well, 0%. So if you want to show this as a fraction, you'd say it's over 1. You could say it's over 240 if you'd like, but it's still a 0% chance that this will ever happen because there's no mangoes in the basket. These are all theoretical probabilities because we didn't actually perform these experiments. Birmingham is late for school and has got to get dressed fast. There are 4 red, 8 yellow, and 6 blue socks mixed up in his sock drawer. Once a sock is selected is not replaced, what is the probability of the following events? Give your answers: reduced fraction and a percent. No problem. Okay. Now again, the first thing I'm going to want to do on this is to figure out how many total socks there are. That will tell us our denominator in these ones. So what do we got? We got 4 red, 8 yellow, and 6 blue socks right here, okay? So as a total number of socks, which is what we need, you got 4 red and 8 yellow, that's 12. And then 6 more would make 18 total socks. Okay, so on this one, remember it's the same as finding the probability of red, and then also finding the probability of red. Now, keep in mind though, it's the second red is dependent on the first one. So, at first when he goes to pick up a red, or the chances to pick up a red sock, there's 4 red socks out of what was 18 socks. But to choose the next one, there's only 3 now red socks out of what would have been 17, because he pulled one out, not only from the drawer, which is now 17, but one of the red socks was taken out. So we got to multiply these two. And for me right now, I'd probably simplify the 3 and 18 right there. They're both divisible by 3, which makes that 1/6. And then the 4 and 6 can also be simplified into now 2/3. So what do we get after simplifying this? In the numerator, we got 2 times 1, which is 2. In the denominator, we got 3 times 17, which appears to be 51. And I believe that's as simplified as we can make it. Looks like we're going to have to need to round our decimal to the nearest tenth, or our percent, because I get 0.039215686, which again, we're just moving the decimal 2 times to the right. So I'm going to make that 3.9%, rounding to the nearest tenth of a percent. Well, what about blue and then yellow? Well, again, we're looking at them separately. First blue, and then yellow. And yeah, the order It doesn't necessarily matter on this one, but it definitely did with the reds. With the blue socks, there's 6 blue socks in the drawer out of what was 18 socks. But when he goes to pick out another sock that's yellow, here there's still 8 yellow socks, but now there's only 17 socks that are in the drawer. So looking at this one, it looks like 6 and 18 can be simplified. They're both divisible by 6, which would make that 1/3. And I don't see that that can be simplified any further. So in the numerator, 1 times 8, which is 8. In the denominator, 3 times 17, still 51. So now it's 8/51. Let's go ahead and put this in the calculator. And I get 0.156862745. Again, I'm getting around that to the nearest tenth of a percent, or the nearest thousandth. So that's 15.7% rounded to the nearest tenth of a percent. So what about the probability of yellow than yellow? Well, let's find out. Probability of yellow multiplied by the proper probability of yellow. There we go. Well, kind of going to work the same way as those red ones did. So we're going to start with, there's 8 yellow socks in the drawer in the beginning, and there's 18 socks. Now, since he pulled one out, now there's 1 less yellow sock, so there's 7 yellow socks to choose from the second one, but also 1 less total sock to choose from. So it's 7/17 right there. Let's go ahead and multiply these out. I see that the 8 and 18 can be simplified by 2. That'd be 4/9 right there. I don't see any further simplification that can occur with this fraction. 4 times 7 in the numerator, that's easy enough, 28. But in the denominator, 9 times 17 would give us 153. Now again, all these fractions you can find if you just put them in the calculators that we have in class. It would simplify those for you directly. But I feel like we can do this pretty easily by hand anyways. So when I put this in the calculator, I get 0.183006536. So rounding to the nearest tenth of a percent makes that 18.3%. So what about the probability of red and then blue? Let's find out. So the probability of red, let's see, there was 4 red socks, right? So 4 red socks out of what was 18 socks. And then the blue socks, there was 6 socks that are blue. And yeah, we didn't take any of those out, but we did take 1 total sock out, so now it's still out of 17 right there. And yeah, we're going to multiply these out. I would still look at the 6 and 18 right there to simplify. They're both divisible by 6, which then makes it 1 and 3. Just makes our multiplication a little bit easier. 4 times 1 in the numerator is 4. 3 times 17, we've seen that already, as 51. So there's our fraction. That is fully simplified. Just need to change that into a percent. 4 divided by 51. I get 0.078431373, which as a percent would be 7 point, rounding to the nearest tenth would be 7.8%. Bren and Ken are randomly choosing pieces of colored chocolate from a bag. There are 6 red, 4 green, 1 brown, 2 blue, and 2 white pieces of candy. Bren chooses the first, looks at the color, then puts it back. And Ken chooses a piece of candy. What is the probability they choose these particular orders? Now remember, since on this one, Bren is putting the one that Bren chose back, when Ken chooses, he's going to find the same total amount of candies in the bag, right? So what do we got on this one? Looks like we got 6 red, 4 green, 1 brown, 2 blue, and then 2 white pieces of candy on this one. So we need to figure out how many total pieces of candy are in here. So, and I know they're chocolates, but you can say candies as well. They're classified the same way anyways. So let's see, 6 red and 4 green, that'd be 10, and then 1 brown is 11, 2 more blues makes 13, and then 2 more white pieces makes that 15. So I got 15 total pieces of candy. That's going to be useful for us throughout. because on this one, for the probability first of blue, I'm going to start with blue. Let's see, there's 2 blues out of 15 candies. Now, since Bren puts that one back, when we go to white here, there's 2 white candies, but still 15 on that, okay? So we're going to multiply these, and again, we want our answers as fractions and decimals. I don't see any cross simplification on this one. 2 times 2 is 4, and 15 times 15 is 225. So this is our simplified fraction, but we've got to put this in the calculator for the decimal, 0.16, which changes into 16%, because we just want the percent. For 225ths, or 16% chance that that happens. Well, what about the probability of green and then brown? Well, green is 4 out of the 15, because there's 4 green pieces, there's 15 total pieces. Now again, that piece is put back, so when Ken goes to choose brown, there's still 1 brown piece, but again, we're looking at 15 pieces. So really these 2 are both independent, because Bren is putting the first piece back on this one. I don't see any simplification on this one. In the numerator, 4 times 1 is 4. In the denominator, 15 times 15 is 225. And we've already done that in the calculator, just like we see above. That is still 16%. So what about red and then blue? Well, I see that there's 6 red candies out of, well, total 15. And then the blues, there's 2 blues out of still 15, right? Because, again, that first piece is put back. And, yeah, there is a little simplification on this one. It's like the 6 and 15. They're both divisible by 3, so that'd be 2/5 right there. I don't see any further simplification, though. So that's going to give us our fraction. In the numerator, 2 times 2 is 4. In the denominator, 5 times 15 is 75. So 4/75. Let's go to the calculator for this one. I get 0.053 repeating. So as a percent, that'd be 5.3 repeating. I'm just going to put 5.3. You can use the bar notation above the 3 if you'd like to be more accurate, but I'm still rounding these to the nearest tenth for me. Then on this last one, we got the probability of white, which is 2 pieces out of the 15 candies. There's our fraction. And then green, there's 4 pieces out of, well, 15. So we're going to multiply these out. I don't see any cross simplification from these. 15 times 15 is still 225. And in the numerator, 2 times 4 is 8. So 8 225ths. Let's go and put this in the calculator. So I got 0.035 repeating. And that would then be I'm going to round that to the nearest tenth, 3.6%. Okay? So you should be able to look at these percentages, right? The higher they are, the more likely they are to happen. The lower they are, the less likely. And just based on the numbers that we have seen from up above here and the total, we should be able to make these conclusions, at least that they were higher or lower depending on these values. But there's our answers. So if Bren eats the first chocolate and then Ken randomly chooses the chocolate, what is the probability that they choose? And we got 4 different situations, but yeah, now the main difference here is that Bren is eating the first chocolate, okay? Now you'll see that when Ken goes to choose his chocolate, of course, now it is dependent on Bren because it's changing the value because Bren is going to keep that chocolate out. He's going to eat it, right? So when we look at blue, it's still 15 total pieces, by the way, so it's still 2 out of 15. But now when Ken goes in to choose the white, there's still 2 white pieces, but now that's out of 14 on this one. All right, so we still need to multiply these out. Yeah, I'd be looking to simplify here. There's 2 and 14. They're both divisible by 2, so that's 1/7. That should simplify it for us. 2 times 1 in the numerator is 2. 15 times 7. Just put that in the calculator. I think it's 105. Yeah, 105. So 2 1/5ths, but we need that as a decimal first to change into a percent. I get 0.019047619, so I can make that 1.9%. Of course, that's rounded to the nearest tenth. Then the next one, brown. So when Bren goes in to choose a brown piece, it's still 1 piece out of the 15. But now, when Ken goes to choose the green piece, well, 4 pieces, but now it's out of 14. So you can compare this with the problem that we just did, and you should be able to see the difference here. And yes, the 4 and 14 are both simplifiable by 2, so that's 2/7. So in the numerator, 1 times 2 is 2. The denominator, 15 times 7 is 105. Yeah, we end up with the same fraction and percent as that first one, just like we did on the last one, but now it's dependent. So now the probability of red, I see there's 6 reds out of 15 total pieces. Of course, that one is kept out. So when we go to brown now, there's 1 piece, but there's 1 less piece in the back, so it's 1 out of 14. Let's go and multiply these. Of course, the numerator 6 times 1 is 6. In the denominator, 15 times 14, let's see what that is, 210. Well, it looks like we could have simplified that. Yeah, the 6 and 210 are simplifiable by 2, which would make this 3 over 105. So what is 3 over 105? Let's find out. As a decimal, I get 0.028571429, which as a percent would be 2.85, so I'm going to round that to 9%, 2.9%. All right, and this last one, brown and brown. So we're still dealing with 15 pieces. That's okay. But when we go in, when Bren goes into the bag first, there's one brown. Now, when Ken goes into the bag, of course, there's 14 pieces because 1 was taken out, but now there's no browns in there, right? So multiplying this one, it's not too bad. 1 times 0 is 0. 15 times 14. Well, it is 210. It's still 0 divided by that, so it's 0, which would then convert into a percent, still 0%, okay? So there's our 4 answers for this one. And that's our objective right there. So that concludes this lesson. Of course, the objective, I can calculate the probability of independent and dependent events. You should feel pretty comfortable with this, especially if you can do independent events. There's no reason you can't do dependent events as well. You just got to, you will have to think about it just a little bit more, but it's definitely doable.